Our next example, I'm not going to go into as much detail as I did in the first one, just so you can just kind of keep getting the feel for this. So I've given you, let's see, the position function. So we have an x of t, we want velocity, and we want acceleration. So remember the slope here, so the slope is the derivative, and that is velocity for position. Just a change in x over time. So let's go ahead and start with that one. Then I'm going to do the derivative d by dt of 3t squared minus 18t plus 6. Pulling the 2 down, I get 6t. 2 minus 1 is 1. Minus, well, t is raised to the first power. 1 comes down, that's just 18. And 1 minus 1 is 0, so that goes away. That's just 1. So evaluating this, then this gives me my velocity at, now let's evaluate it at 5 seconds. That's what that in the parentheses means. So we get 6 times 5, not 50. 6 times 5 minus 18, otherwise known as 30 minus 18, equals 12. So what do I have? What is this? This is 12 meters per second. So that says that I have this velocity change happening between 0 and 5, and I'm going 12 meters per second at that point in time. Now acceleration. Well, let's see. I have the velocity from here. I can't do anything else with that graph. So just taking the integral of that's not going to get me what I want. What do I have now, though? I have a v of t now equals 6t minus 18. So if I want acceleration, I just take the derivative again to get that. So d by dt of 6t minus 18. So the derivative of t is just 1. 1 comes down, 1 minus 1 is 0, right? So that's going to give me 6, and that's a constant. Derivative of constant is 0. So that's it. No math. 6 meters per second squared. And I'm done. I've answered both of the questions. So at 5 seconds, I'm going 12 meters per second, and my acceleration is 6 meters per second squared. Let's do one more, where I have a of t equals 6t minus 18. And I know at t equals 0, v of 0 equals 24. We want the velocity at 4 seconds. Okay. I have what here? If I do the derivative of that, remember that gives me the jerk. So integrating the area under, so doing that is not an integral. Doing the integral of this of acceleration will give me velocity. And I gave you this example because here we have an initial condition. Remember I said before we can ignore that constant most of the time, but here I have to look at this, and once I do my integration we'll talk about how we're going to deal with that. So I need to integrate this. So I have a of t, let's do that in a different color. The integral then of 6t dt minus the integral of 18 dt. So that's going to give me, let's see, I have just one there. I need to increase the exponent. So the first part is going to give me t squared. Let's divide by 2, and remember that I have a 6 in front. We'll simplify it after. And then the other one, well, there's a t to the 0. I'm adding 1, so that's just going to become minus 18t. Now let's simplify. So I get 3t squared minus 18t. Now, there's that pesky little plus c. So I know that v of t equals this 3t squared minus 18t plus c. Now is when the initial conditions come in. I'm told that time t equals 0, I have this velocity of 24 meters per second. So what I'm going to do is just put zeros in all of this. So if t equals 0, that goes away, and I'm left with v of 0 equals c. Well, I know at time t equals 0, I have 24 meters per second. So that is my constant. So in the end, all of this gives me a function for v of t to say that I have 3t squared minus 18t plus my 24. Cool. Now I can just go ahead and put my times in. So what did I want? I wanted v at 5. So let's go here, equals 3 times 25 minus 18 times 5 plus 24. So how fast am I going? 3 times 25 minus 18 times 5 plus 24. Gives me 9 meters per second. And there you have it.